here. So first of all, we'll go back to the title slide here. I'm Schmandt with Ovintiv, and I guess on behalf of ARMA and the Technical Committee on Induced Seismicity, chaired by Ahmad Ghassami and assisted with Jens Lindstern and Madi Haddad, we welcome you to our monthly webinar series. So today we're very excited to have Margaret Glasgow and Brandon Schmandt talking about Raton Basin. So very interesting case study with, I guess, a long history, as I think we'll hear, of induced seismicity. So it'll be good to, looking forward to an update on what's happening there and hearing their the latest and greatest on this sequence. Before we pass it over to Margaret and Brandon, just a few introductory remarks, and I'll pass it over to Jens to talk about the upcoming schedule.
Yeah, thank you, Sean. We have two talks scheduled coming up. Mike Brzezinski will be speaking not the first Friday of October, actually that's the second Friday of October, on the 13th. We had asked him if he would speak about the recent seismicity that's happened in Ohio, but he was particularly interested in talking about the much greater amount of seismicity happening in central and northern Kansas, which is an interesting area to think about induced seismicity. So that'll be I think of interest to a lot of you. Still working on November, the first Friday, but we have some interesting ideas, including about geothermal panel. So stay tuned. And then Paul Siegel of Stanford's SCITS Consortium will be speaking on the 1st of December, same time as usual, 10 a.m. Central.
Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. First of all, thank you so much for joining us for another webinar on induced seismicity by Margaret Glasgow and Brandon Schmandt. First of all, please feel free to share the webinar invite with the colleagues that are interested in this topic. We would like to send out these notifications to a wider community and have a platform here for better interactions between the interested parties. And please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window. And please send these questions to everyone in order for us to summarize the repetitive questions and use the time more efficiently. This specific meeting is recorded after consultation with the presenters, and this recording will be uploaded after this meeting in our Induced Seismicity Technical Committee YouTube channel. The link to this YouTube channel is in the invitation email. Please subscribe to this channel for the future notifications. Without further delay, let's invite Margaret and Brandon to take over the stage and present to us. Thank you so much, everyone.
Hi, can you see everything?
Yes, everything is good.
Okay, great. Thank you for the introduction, and thanks to the conveners. This is a great webinar series, and we're excited to be presenting today, Brandon and I. So yeah, we'll sort of switch off in the middle, and Brandon will talk for the second part of the talk, and then there's 3 parts to the talk. I'll talk the first and the third part. And so yeah, we'll be talking about complex faults and some interesting earthquake sequences in the Raton Basin. This work wouldn't be possible without contributions from Risha Wang. And also a lot of the data that was used to come up with these projects is from a small array that the University of New Mexico put out in 2016, as well as a nodal array that was out for a month in 2018. And sort of the common thread for all of us is the University of New Mexico, where I recently finished a PhD, but I'm now at USGS. Brandon is still there as a professor, and then Rija was there as a postdoc, but now she's at SUSTech. Let me just get the laser pointer. Okay, so as I mentioned, the talk is split up into 3 parts. The goal of the projects were to document the seismicity in the basin in order to increase our understanding of the reactivated faults there, as well as earthquake sequences. So I'll start in the first part by talking about just a general introduction to the basin, and then review a few of the new earthquake catalogs we've been able to build. And then Brandon will take over and talk about the faults that we've identified from those catalogs, and then some of the interesting slip we've seen. And then lastly, I'll talk about the third part, which is revisiting this interesting earthquake sequence for the largest event in the basin, which was a magnitude 5.3 in 2011. Okay, so just an overview of the basin. It's about 50 kilometers wide and 100 kilometers long. It's located on the Colorado-New Mexico border right here. It's sort of at the intersection of 2 large stress fields, which are the Rio Grande Rift towards the south, and then the Great Plains towards the east. From this map, you can see, using the legend, the extensive faulting, folding, and magmatism that's happened. It's also a region of high heat flow, sort of in some sections on par with geothermal settings. And then lastly, something we find interesting is that helium-3 plus is found in nearby springs, natural springs, and production wells. And this is sort of interesting because it suggests that there was a permeable path at some point between the mantle and the surface. Okay, so jumping into what we're here to talk about, which is the seismicity and the wastewater injection. So people are familiar with this plot to the top right. Down at the bottom right is showing a figure that's similar, but just for the Raton Basin. So the number of magnitude 3 or greater earthquakes per 6 months are shown as these black bars, and then also the wastewater injection is shown as this blue line. So this is a sum for the entire basin. I should mention that the basin is a methane production field, and the wastewater is a byproduct of the methane production. So back to this plot, you can see that the wastewater injection really started taking off in the 1999, and was immediately, or within a year, followed by a peak in seismicity. And then the wastewater injection sort of plateaued and peaked in 2011, which is also where we see a peak in the seismic record for the number of magnitude greater than 3 events. And also the largest recorded event was in 2011. But since 2011, the wastewater injection has been declining, so for about the past decade. And another kind of interesting thing when we consider the Raton Basin compared to the central US is that the peak in size, or the onset of seismicity, is about a decade prior to the onset for the central US in 2010. So the onset in the Raton Basin is in 2001. Okay, so looking at where those earthquakes are found is mostly in these 3 zones. This is a map showing the earthquake locations just from the USGS catalog for 20 years. This is a sort of a difficulty in studying areas of induced seismicity, is the low instrumentation when the seismicity turned on for areas in the central United States. So for example, there were 0 stations within 100 kilometers prior to 2008. In 2008, the transportable array passed through, and a single station was left as a legacy station that's been continuously recording since then. And then in 2016, I'll talk about the increased instrumentation that we put in at the University of New Mexico, myself included. There have been a few studies that were able to document the seismicity during periods of temporary denser instrumentation. And those studies identified some faults in more detail using earthquake locations. And so each of these three zones, you can see the seismicity is sort of linear, and these lines are interpreted to be single through-going faults. So each zone is suggested to have about an 18 to 15 kilometer long through-going normal fault. So then what we're going to be talking about for a lot of this talk is building new earthquake catalogs to increase our understanding of the faults in those three zones. And one way that we're able to sort of increase our knowledge in these areas is by increasing the instrumentation. So in 2016, UNM put out 7 broadband seismometers, the white triangles shown here. They're 3-component. They've been recording continuously since 2016. 3 of them are telemetered and stream data to USGS, and then the other 4 have data that's manually collected every 6 months or so. And then in addition to the broadband array, there was a 96-node geophone array that was installed for 1 month in 2018 in the southern part of the basin. And then if you want to see sort of the times that correlate to those, you can look at this plot here. So since 2016. And then lastly, there's 30 wastewater injection wells that have data that's publicly available at 1 sample per month, and that's the injection volume at each well. All right, so we use when we originally started building the catalog in 2018, we used a traditional workflow, Antelope, which uses a short-term to long-term average phase detector, an association step, and then manually refining the phase picks. However, a bunch of machine learning algorithms were sort of coming out at the time, so we adapted our workflow to try one of these, and we used PhaseNet to get the phase picks, and then we used Real to associate the picks and update the locations, VelS to update the locations, and then for the relative relocation step, depends on which study we'll be talking about today, but we either use GrowCluster or HypoDD. And on the right is just showing an example of how PhaseNet works, and the blue lines are showing the P-picks, and at the bottom is showing the probability of that being a P-pick, or the red lines are the S-picks and the probability of that pick being an S-pick. And so since we had picks using these 2 different approaches, we were able to compare them. We compared 50,000 picks between the machine learning and traditional approach. And on the right are showing a comparison for the P phase at the top and the S phase. And you'll notice if you look at the x-axis that the picks agree within 1/10 of a second for both 95% of the picks agree within 1/10 of a second for both the P and the S phase. And so the darker gray would mean that the human pick was earlier. And so what you can see in both the cases is the machine learning pick was slightly earlier than the human pick. We move forward with the machine learning approach, or the machine learning built catalog, because there's 5 times as many earthquakes in it. Okay, so here's an introduction to one of the catalogs that was made. This is for the there's sort of 2 different views. So really dense instrumentation for a short period of time. So in this case, this catalog was made using the 96 nodes for 1 month in 2018. This is showing a few of the different steps. But the final catalog is here on the right after HypoDD. You can see the seismometers, the triangles here, and the earthquake locations colored by depth. And ultimately, this catalog had 10,000 earthquakes. They occurred 4 to 6 kilometers below sea level, and the magnitude of completeness during this 1 month is -0.5. And we'll try to keep a figure like this going, because we'll talk about different parts of the basins in this talk, and the black box is highlighting whatever we're showing on that slide. And so the other catalog that we'll be talking about in the beginning, or the first 2 parts of this talk, is this 4-year catalog with 8 instruments, so a very different view, many fewer instruments, but a much longer time period. And so on the left is that plot from USGS, looking at the earthquakes that they were able to detect over 20 years. But with our denser instrumentation, different method and a very different goal, we're able to detect many more earthquakes. So we found 38,000 earthquakes over this 4-year time period. The earthquakes occur from 3 to 6 kilometers below sea level, and the magnitude of completeness is 0.6. And so immediately just want to mention that we found seismicity in 2 of the 3 previously identified zones, and that nodal footprint falls within sort of these 4 broadband stations. So that's also where it was sensitive to seismicity. And so part 2 of the talk, we'll be looking at the faults in these zones and slip. And then part 3, we'll be looking at why we didn't find seismicity in this 3rd zone. But before I pass it over to Brandon to talk about the faults, just wanted to present one point. So we were curious using this catalog here from the broadband array over the 4-year time period, if induced and natural earthquakes are different. So we looked at a few simple statistics just to see if there was anything sort of special about the induced seismicity. And so I'm only going to review a few of those, but the first thing we looked at was the decay of the magnitude frequency distribution, also known as the B value. The B value was 1.0, so basically perfect. And this is similar to the B value that's found in purely tectonic settings. So we didn't find like particularly swarmy earthquake sequences, at least on the scale that we looked at. And then another thing I wanted to mention was that we modeled the earthquake rate using ETOS, which works very well for tectonic sequences where you have main shock, aftershock earthquake interactions. And so the red line is the observed earthquake rate in the basin, and the white line predicted from ETOS plots basically on top of that and matches it very well. So ETOS was able to fit the earthquake rate in the Raton Basin well. And so the statistics are indistinguishable for this area of induced seismicity compared to those, or indistinguishable from those found for tectonic settings. And we think that this implies that the earthquakes are releasing predominantly stored tectonic stress. Okay, now I'm going to pass it over to Brandon for the second part.
Sure. So we'll zoom in on some of these faults and take advantage of the catalogs Margaret just introduced, and mostly focus in that southwest part of the basin to start with, and look at the most active faults during 2016 to 2020. And so we'll see those on the next slide. Cool. So this is showing pretty much all of the basin on the left side and the absolute locations. So these are after using real and then VELS to get the locations. So this is the 38,000 earthquakes on the left. And then after relative relocation here using waveform cross correlation through the GrowClust package, we lose most of those smaller groups in the north. We're just showing clusters that had correlation coefficients higher than 0.5. And going forward, we're going to focus on clusters that had more than 100 earthquakes in them. And so we're going to lose most of the north part of the basin there. And some of that is dominantly that there are fewer earthquakes. And then for some of the earthquakes near the northeastern edge of the basin, we're also, we don't have quite as good a station coverage. And in terms of the depth here, just to orient things, a lot of the production here for coal bed methane is very shallow, a few hundred meters sometimes. The injection depths below the surface are typically in a range of 1 to 2 kilometers, mostly 1 to 1.5 kilometers below the surface. And then the top of the basement does have some topography here, but in the central part of the basin where it's most active, the top of the basement is probably about 2 to 2.5 kilometers below surface, or very near sea level. And so those ranges are shown in the blue and the gray on the right. And so most of the seismicity starts kind of right near the the sediment basement boundary, but it peaks a couple kilometers below that, more at about 4 to 6 kilometers below sea level. Okay, and so we'll look in more detail at the lower left part, the southwest part that's most active, so we can look at those relative relocations. And on this map, the relocated clusters that have more than 100 earthquakes are colored here by strike. And we can see this is quite a different view than 8 to 15 kilometer long through going normal faults in each box. And they're not strictly north-south, although there are north-south oriented faults among the cumulative distribution here. But most of the seismogenic segments from 2016 to 2020 are about 1 to 3 kilometers long, and they have this range of orientations. And so if we look at the distribution here, just shown in a rose diagram, most of these range from having strikes of north-south, kind of as expected, but then we find a maybe larger distribution than one might have expected of approximately northwest-southeast striking fault segments within the southwestern part of the Raton Basin from 2016 to 2020. And so, one of the questions here, we have enough sensitivity to detect 38,000 earthquakes with these total of 8 broadband stations, but it's obviously not incredibly dense coverage or ideal azimuthal coverage. And so we want to look at do fault plane solutions support that there are a range of strikes among the seismogenic faults here during that time. And so we'll look at some of those next. Okay, so the beach balls here come from Rija Wong, and these are from 1D waveform fitting based moment tensor inversions. In this case, they're deviatoric moment tensor inversions, and we have those for about 30 earthquakes. Those are the ones, the red and white beach balls. I'll mention the purple ones in just a second, but there are about 30 of them for the red and white waveform inversion based beach balls. And they do predominantly show northwest southeast to north-south strikes. There are some exceptions, but in the southwest part of the basin, where our stations are a little more closely located to the seismicity, there is pretty good agreement between the fault strikes from the hypocenters and the fault plane solutions. There are some areas on the edge of the basin where that agreement is not so good, and so we could mention, say, all the way in the north near the Spanish Peaks. There's a sense of a northwest southeast strike just from the hypocenters, but we get a pretty much orthogonal indication from 3 moment tensors up there. And so there's our main thinking is that we don't have excellent azimuthal coverage on those hypocenters. We can detect the events, but there may be some bias there in the hypocenters, and we'd probably trust these beach balls a little bit more. I should add that the beach balls for these waveform inversions are only for magnitude about 2.8 and greater events, and so that's why there are only 30 of them. We were also very curious about some of the events that showed different strikes, and so 4 of these purple beach balls shown here are for first motion polarity fault plane solutions, and they do corroborate some of the northwest southeast striking fault segments, particularly in the middle box shown here. And we're going to look at that region in more detail with the node array in just a second. Okay, so this is the detailed view, and this is predominantly work from Rija Wong. She did a great job digging through all the data from the node array. It was just a month of data, but about 10,000 earthquakes total, as Margaret mentioned. And just from her description of this, we're going to look at some different clusters that are here colored and numbered. So C2 is right near the Colorado-New Mexico border. This one I'll consider as kind of an example of more complicated faulting in the Raton Basin, where we see multiple fault strands with different orientations very close to each other, and that is more challenging to interpret structurally. And then there are also some simpler cases. I'll highlight C3 in the sort of yellow color here. And in that one, it's a much simpler fault that shows a dominantly planar structure, strikes north-south. It's kind of everything we expect. And on this map, there are about 100 beach balls that are from first motion polarity picks from the node array, which had very clean onsets. There were typically a dozen or more stations within just 5 or so kilometers of the epicenter, and so we had pretty good coverage on these. And so if we look at C3 here at the bottom, you can see that we're getting pretty consistent focal mechanisms for this north-south striking normal fault. And then we have the two cross-section views, and the colors on the cross-section views are just by time. And so we can see the earlier times in the deployment are blue. And so you can sort of watch in this sequence, the earlier earthquakes were a little shallower in that cluster, and then they propagated to about 2 kilometers deeper over that month. And the 2 largest earthquakes during that month were approximately moment magnitude 2.8 or 2.9. And so we're going to look at these a little bit more. So sometimes these spin and sometimes they do not, but we'll kind of roll with that. So the one on the left, C2, is the example that's a little more complicated. Doesn't have quite as many hypocenters in it, but I would argue there are 3 different fault strands here, and this whole box is only 1 kilometer wide. And so these 3 fault strands are really within about 500 meters. And we're seeing distinct focal mechanisms on these 3 fault strands, as well as the distinct waveform clusters from GROW-CLUST and their relative locations. And so I think we're seeing a range of activity very close, within about 500 meters here. And then on the right, C3 looks like a very well behaved, nice normal fault, pretty planar structure, is interesting propagation, spatial temporal propagation of activity along that planar surface, but it's a pretty planar surface and agrees very well with the regional stress field. We can move on to the next slide. So C2, the complicated one I was mentioning, another complication that arose that Regia picked up on very well is that if we were to look at the correlation coefficients between events, we sometimes saw very high negative correlation coefficients. And so this correlation matrix you're seeing here in the middle with the blues and the reds, dark red is a correlation of 1, and dark blue is a correlation of -1. And then some of the representative waveforms are over here on the left. And so there are these clear polarity flips for events that we're locating only about 200 meters apart or less in some cases. And at first, when we zoom out and look at this on the map, we think, all right, we have these reversed polarity focal mechanisms and these clearly flipped waveforms. They do have different character, that the ones that are apparently reversed, shown in blue, their waveforms have very weak coda, whereas that's what we'll call the normal polarity, or the red ones, just because they're a bit more abundant, they have much stronger coda in their waveforms. So there are some other waveform differences, but just based on the first motion polarity picks, we come up with basically opposite fault plane solutions. And so, zooming out, you could look at this as, is there potentially reversing slip on this fault? But if we zoom in and look at these locations and look at the spatial temporal evolution here, we see that all the apparently reversed polarity earthquakes are spatially clustered and likely defining a distinct fault strand that's just separated by something like 100 to 200 meters distance from other faults nearby. And so I point this out because it's pretty challenging to then interpret, if you can't see these structures at something like 100-meter resolution, we could perhaps be tricked into thinking that this is actually reversing the slip direction rather than being a different fault strand right nearby the more active fault. Let's go to the next slide. And so this is another view of that cluster we mentioned before, and we saw the little movie. It was kind of 3 different subclusters of seismicity. You can see those on the left. And then you can also see the events that have focal mechanism solutions. And so there are some events in each of those 3 clusters. And so we're able to see the different fault plane solutions defining the 3 clusters, as well as the spatial separation and waveform similarity separation determined by Grosclust. And then the fault plane solutions are shown in the middle panel, and then back over to the hypocenters on the right. And I would say, a tentative structural interpretation is that by having this fault branching at something like 100 to 200 meter scale, we could be seeing what looks like apparently reverse slip, but we're actually just moving across a more complicated branching structure, such as the one shown here. We can't see it in incredible detail, but it's pretty interesting, I think, for a month of seismicity and being able to resolve that there might be multiple fault strands there rather than reverse slip. Okay, so I think we've seen that there are a range of strikes here, and why those are all active in the same region, how those could all be pushed toward failure by injection is an interesting question. And so we want to consider, at least briefly, how these fit with the regional stress field. And I think the Raton Basin is a particularly interesting area to look at stress indicators. And so we'll take a look in the next couple slides. Okay, so this is from Lundstern and Zobak, 2020 on the left, their compilation showing a bit larger scale, Rio Grande Rift in the middle. And we see, dominantly north-south maximum compressive stress orientations, and then transitioning out onto the plains, they rotate more toward east-west. And in the Raton Basin, we're looking at a pretty tight sort of corner where both the north-south orientations and near east-west orientations are present. It's not as densely covered as we might like in the interior of the basin, but on the Colorado side of the border, we see dominantly north-south maximum compressive stress orientations. And on the New Mexico side, it's more toward the southeastern edge of the basin, but there are multiple stress indicators that suggest SH max has rotated to being closer to east-west. So there's almost a 90-degree rotation that occurs somewhere in this area. And so perhaps it's not too surprising that we are seeing some diversity of fault orientations that could be activated by wastewater injection. And so this is going back to the relative location catalog and the moment tensor solutions, and just seeing that, okay, well, maybe this does fit. It's not too crazy that it's different from our initial sort of large scale view from things like the transportable array data that were 70-kilometer station spacing, or the very sparse public data earlier in this earthquake sequence that led people to think maybe there are just 3 large approximately north-south normal faults. We think that the observations we have, at least showing here from 2016 to 2020, support a pretty wide range of fault orientations being active, but they're mostly short fault segments. And here we'll pass it back to Margaret to take a look at that third zone that we haven't really talked about, but hosted the biggest earthquake earlier in the Raton Basin induced activity.
Cool, thanks, Brandon. So yeah, I'll talk about the zone that Brandon just mentioned, the Trinidad zone, that had this large earthquake, but has also been apparently not as seismically active recently, and kind of discuss those two things. First, as I just mentioned, the seismicity in this third zone, the Trinidad zone here. So Brandon was just talking about these two zones where we found a lot of seismicity in the 2016 to 2020 time period. But in this third zone, the Trinidad zone, we did not see very much seismicity, a handful of events per year. This is zooming in on that. But the zone was previously active, such as in 2001 and 2011, where there were these aftershock deployments that were able to detect seismicity related to the 2011 magnitude 5.3 main shock and the 2001 magnitude 4.5 main shock. But as was mentioned earlier in the talk, the instrumentation is variable, so that's led to an incomplete record of the seismicity. The area appears to turn on and off, but we wanted to look at this in more detail and try to get a more complete catalog. A few more details about the magnitude 5.3 earthquake. There was a geodetic study following the earthquake that inverted for the slip from the INSAR data, as well as using the earthquake locations. And they estimated that the rupture length was 8 to 10 kilometers long, which was anomalously long given the magnitude of the event and faulting style. A more normal rupture length would be like 5 or 5.5 kilometers. And so because of the long rupture length and the magnitude, the event was suggested to have a low stress drop. So a few of the questions for this part of the talk are looking at the magnitude 5.3 earthquake in more detail. Why was the rupture length anomalously long? And then another broader question is, why did we observe so few earthquakes in this zone in its recent history? So the instrumentation guides our method for this study. So as I mentioned earlier, there's sort of sporadic instrumentation in space and time. So the seismometers nearby on the day of the 2011 magnitude 5.3 included one instrument at the edge of the basin, the Legacy Transportable Array Station. And then the next closest instrument was 100 kilometers away. So there's very few instruments that were out on the day of the magnitude 5.3. However, the day after the 5.3, there was a rapid deployment with these 4 stations here that recorded for about 10 months following the main shock. And so a summary of the methods can kind of be introduced using this map of the seismometers and when they were deployed or recording. So the first thing we do is build an aftershock earthquake catalog using these 5 stations that were out for 10 months. And we use a machine learning approach. And then we build templates from all available sources. Many of the earthquakes are from that aftershock catalog. And then we build a template detected earthquake catalog using this single TA station that was recording for 14 years. So that's how we can get at the evolution of the seismicity in the zone for a 14-year time period. Okay, so I'm not going to review this because I've already talked about it, but we basically use this machine learning workflow that I introduced in part 1. So taking a look at the aftershock catalog, we detected 3,500 earthquakes. The majority of the earthquakes fall into 7 clusters, so 95% of the events. Here you can see that there's an easy place to sort of split the catalog where we have more than 100 events in each cluster versus once we go to the 8th cluster, we only have like 15 or 20 events. On the right is showing a map of the seismicity. So we're zoomed in pretty close. Here's a scale bar showing 5 kilometers. Here are the seismometers, the black triangles, the wastewater injection wells or squares. And then the 7 main clusters that we're focused on are colored by each cluster, one color, and also labeled. These 2 clusters in the north, they overlap in the map view, but they're easy to distinguish in their depth field. And then another thing to note is the main shock epicenter plots down here to the south near cluster S1. And initially when we got these results, you can see that the area looks fairly segmented, which we had seen in other zones, and just sort of highlights that faults can be complex, as Brandon just presented. This is just showing an example of fault breaching with depth from a fault in New Zealand, and just thinking about how do these sort of extensive faults get reactivated and which segments get reactivated from wastewater injection. Also, slip can be complex. Ridgecrest was a good example of that, where multiple fault segments can slip in a single event. So just two things to keep in mind when I show the results in more detail. So after we had the aftershock catalog, we built a template detection-based catalog. Here's just showing an example of one of the templates and a few of the detections we had that resulted from using the template detection. And we only look at events with cross-correlation coefficients above approximately 0.5. So this would be at the lower side of our detection threshold that we used. And so we used templates from all the available sources to try to track the seismicity in that Trinidad zone. Okay, so this is similar to the plot or the map I just showed, but removed and added a few things. So here you can see the 7 clusters clearly by color. Here's the main shock, which now has a focal mechanism, and also foreshocks and aftershocks that were large events with focal mechanisms nearby are plotted in this view. And then importantly, the rupture area from the geodetic study is shown as a dark gray box, and the maximum slip patch is shown as a red polygon here in the center. And so now we're gonna really zoom in on this one event and look at what we found using the template detection catalog. So this is showing plus and minus 24 hours on either side of the magnitude 5.3. So the 5.3 is in the center right here. So this is a timeline. The seismicity is bend in 30-minute segments. So each bar is for 30 minutes. All the larger events are labeled at the top. So the foreshocks and the aftershocks. And the colors here correspond to the map over here. And also for the foreshocks that had high enough cross-correlation coefficients, the edge of the larger events, if they correlated, they'll be the same color as that cluster. So blocking off sort of the right side and focusing on the time before the main shock, what we see is that we see these cooler colors here, which is telling us that the foreshocks are isolated to these southern clusters, which are these blue colors. We think that this is good evidence for the cascade up model, where basically earthquakes are, or the foreshocks are testing the strength of these fault segments, and the main shock is able to happen once favorable conditions are met for continued slip. And I just want to note the increasing seismicity prior to the main shock, as well as this large foreshock that was 6 hours ahead of the main shock. There's very few observations, as I mentioned, of the during the time of the actual main shock. So during that 2.2 second rupture time, we did the best we could. We can't have a source time function. We only have one seismometer 30 kilometers away. But we looked at the envelope function of the waveform. The gray is highlighting that 2.2 second rupture time. And we see multiple peaks in that envelope. And we think that this is supporting evidence for the rupture of multiple segments. And then also the maximum slip patch is closest to S3 here. And then looking at the time immediately after, so one day after the main shock, what we see is these 4 segments to the north, which had been inactive, are activated within 60 minutes of the main shock. And we think that that's due to triggering from the main shock event. And then also seismicity continues on these 3 southern segments. And so sort of synthesizing all of this information, what we suggest is that the main shock ruptured on a southern fault. This is just sort of a cartoon image of a planar fault, and then triggered seismicity on a northern fault. If only the southern fault ruptured, this would suggest that the main shock rupture length was normal, about 6 kilometers, and that the event is not necessarily a low stress drop as previous people had suggested. And then additionally, just another note is that the rupture may have arrested due to a structural complexity, such as maybe a bend or an intersection. This could be another fault right here, or there could be a bend between S3 and N1. Okay, and then for the final part of the talk, looking at the template detection catalog over that 14-year period to try to get an idea of why from 2016 to 2020, we saw such a small amount of seismicity in the Trinidad zone shown by this black line compared to the 2 other zones. This is a log scale plot. Okay, so this is the first look at the 14-year temporal evolution of seismicity in just the Trinidad zone. You can see pretty clearly this increase in the earthquake rate associated with the magnitude 5.3 earthquake sequence. And seismicity sort of continues in the zone, which you can tell by this increasing slope of this line. But then by 2016, this line is basically flatlined, and the zone is essentially seismically quiescent. And that continues up until the study goes to mid-2022. So the first thing we wanted to look at was the wastewater injection. And this map has maybe a few more details than we need. And I'm going to cut off part of the wastewater injection and just look at the time where we have this template detection catalog, which is 2008 to 2022. So the blue is showing sort of the southern segment of the 2011 earthquake sequence, so the main shock area, and then these red earthquakes are showing the northern part of the 2011 sequence, and the black dots are showing the earthquakes associated with the 2001 sequence. And then the wells are the squares here. You can see there's 2 wells in this 2001 sequence, 1 here, and then 2 co-located wells a few kilometers from the magnitude 5.3 main shock. And so here the colors correspond between these 2 plots. You can pick out whichever wastewater injection rate you want to look at, but the top gray thin line is showing the summed rate for the whole area. And so you can see the time of the magnitude 5.3 main shock, and within about a year of that main shock, the wastewater injection rate decreased to about half of what it had been. And we think that is part of the reason why we don't see very much seismicity in this zone, although it takes some time before we see the effect of that. So we think the decrease in the seismicity is due to the significant decrease in the wastewater injection, but also due to the slow accumulation of tectonic stress on those faults. Okay, and then a very final sort of cliffhanger, I'm going to call it. So recent seismicity in the Raton Basin. So updating this plot that I showed in the beginning of the talk, just to highlight something that's been going on recently, which is that the earthquake rate has been particularly high in the first 6 months of this year. So there's been 14 events. This makes it the most seismically active time since the 2011 magnitude 5.3. And then in the second half of 2023, so far, there's been 5 more earthquakes. And where those events have occurred are sort of on the outside of the Trinidad zone in sort of new areas. Yeah, and I don't have too much more to say about it. I haven't updated the wastewater injection rate, but just from a first look, it doesn't look like there was any huge change in the wastewater injection, like a significant increase. Okay, so then for the conclusions, short faults with variable orientations host seismicity in the Raton Basin. The earthquake statistics are indistinguishable from tectonic earthquake statistics. The 2011 magnitude 5.3 main shock ruptured multiple well-separated segments. The Trinidad zone has been seismically quiescent since 2016, and 2023 is on track to be the most seismically active year in recent history, at least. And maybe the broader picture takeaways or things to think about, or how, you know, this could inform other areas is the Trinidad zone provides an example of the cessation of seismicity in an area that previously hosted multiple large earthquake sequences. Moderate magnitude earthquakes can have multi-segment rupture, and seismicity persists despite a decade-long decrease in wastewater injection. Yeah, and that's the end of our talk. Thanks so much for coming. We look forward to answering the questions, and if we don't get to your questions, please feel free to email us.
Great. Well, thanks, Margaret and Brandon. Really interesting case study. You covered a lot, and I'll maybe kind of help ask some of the questions here. But before I go to the chat window, I'll maybe ask one of my own to give participants a moment to enter questions they might have. But Margaret, I guess looking at that third area that you talked about and going back to the original geodetic modeling from INSAR, do you think it's possible because of the INSAR cycle time between panels to get the INSAR data? Could it be an integration of both the 5.3 and some of the aftershock sequence that you identified that's being modeled, sort of a summation of the 5.3 plus aftershocks?
Definitely. So, you know, we're looking at a much finer temporal scale with the seismicity, and for the INSAR data, it's sweeps that are multiple months apart. So we think that, you know, the INSAR accounts for all of the deformation of the full sequence. So that includes the magnitude 4.7 foreshock, and then also that triggering that we showed to the north, which really like almost doubles the extension of the length. So
interesting. And I think I'll use one of Stan Wasowski's questions in the chat window and maybe expand it a bit to just kind of ask you about you and Brandon about the potential induced component of this. So for this particular, the third part, you kind of nicely hit on the injection sequence, but it looks like things are pretty tightly spatially controlled with the injection wells, as Stan points out in the chat window. But for the other two parts, the sequences that Brandon was talking about, for instance, for the fault segments, is there good spatial and temporal association with wastewater disposal for those segments?
Sure, I can try that. And I think the most relevant figure we know is very early on in the talk, the sort of summary of kind of 2 decades of pumping and M3 plus seismicity. You know, we don't have continuous monitoring at local scale across this. And so that magnitude 3 and up view is the only sort of consistent baseline we have for the seismicity. And there's a nice correlation, of course, with the onset. You know, in hindsight, it's much clearer than I think it was to people looking at it, you know, circa 2001. But the injection really picked up in the early 2000s. The first larger earthquake occurred in 2001. And then, you know, magnitude 3 plus seismicity continued at least at an elevated rate prior compared to prior decades. But within that time, you know, once the basin sort of turned on, we have looked for and not found any, you know, statistically significant correlations during time periods such as, say, 2016 to 2020. There's a gradual decrease in injection volumes in general, but they're pretty steady. I mean, the decrease is on the order of 20% over 4 years, so it's not very dramatic. And yet seismicity would move around between those clusters during that time, not with any apparent correlation with small scale variations in injection rates on different wells. And so the onset of seismicity seems to correspond very well with within at least a couple of years of the onset of larger volume injection. But once it's going, it seems a bit more chaotic as to how the earthquake rate is evolving and which fault segments are active through time. It seems to be in more of a statistically steady state where it's all active, but it's moving around the basin, and it doesn't seem to exhibit, say, month to month or quarterly kind of scale correlations. We haven't seen evidence of that.
Have you had a chance to look? I don't know if there's any kind of public domain injection pressures that might be informative in terms of changes in injectability of these wells.
Yeah, I'll probably pass that to Margaret in just a second, but give her a touch of warning. This is based on whatever's in the Colorado and the New Mexico databases, and dominantly in the Raton Basin, this injection is under gravity feed. And for the most part, there are not reports of large increases in bottom well pressures. So the unit seems to take about as much water as they want to give it. But there have been isolated times where there have been reports of injection under some pressure. And, Margaret's dug through those records more than I have, but, sometimes the pressure data are added a little while after, and I'm sure it's difficult to keep up with these records for all these different wells, but it appears like there are isolated times that there is some injection under pressure, but I don't remember those pressure numbers off the top of my head. But the majority is under gravity feed. Anything to add to that, Margaret?
I mean, not I'd say not really. I've really dug through like uploaded PDF records with people's notes on them and different pressure tests at different wells, especially the ones that I think are kind of interesting. But there's a lot of jargon, and I worked in oil and gas for a bit. So, trying to understand what's a test and what's injecting under pressure, it can be difficult. So I think, that's not something that they necessarily are reporting when they're reporting it. It's normally a report of no pressure or zero. So I think Brandon summarized it well. But if you really want to get into some super fine details, we could always talk later.
Sounds good. So going back to the chat window. So Adam Begg has a question. He's wondering about the low apparent stress on the 5.3, and any comments just in terms of seismic efficiency? Do you think it's enriched or depleted in terms of the amount of radiated energy?
I'll take a swing at it. So I think that from our study, we think that the event was fairly regular, nothing too special besides the location and being really near a wastewater injection well. The previous study had suggested that the event was potentially low stress drop, or not really along. Because of the rupture length, they suggested that the event was low stress drop, just kind of considering a 10-kilometer rupture length and a magnitude 5.3. But we suggest that the rupture length was probably fairly normal. Yeah. I hope that answers most of the question.
Sure. I'd just add, I think you were right on target, Sean, with your comment earlier about just the temporal integration of the INSAR. So this estimate of a 10-kilometer long fault, which then makes it seem anomalously low stress drop, that was integrating many earthquakes that occurred over multiple months. And so zooming in Margaret's catalog with better temporal resolution, I think we're just saying, well, actually only about 6 kilometers ruptured in the 5.3, and the rest of that rupture happened afterward, dominantly in the days right after the 5.3, when the northern 4 segments were activated. And so we don't think it's an anomalous stress drop at all. It could fit in a sort of garden variety 1 to 10 megapascal kind of range.
Great. And I guess moving on, Neil Watson has a question, and I'll maybe just generalize it a little bit. Just in terms of kind of the structural geological setting, some interesting observations, particularly from what you described, Brandon, looking at those different segments. Any comments on sort of extending the interpretation of those different segments by leveraging traditional structural geology are these all kinematically consistent, I guess, to ask it another way?
Yeah, so I should have mentioned that more, but there's very little known about, the faults that I'm looking at are not mapped at the surface, and at least in the open access academic literature, there aren't, to my knowledge, and I'd love to see it if someone has it that they can share. Balanced structural models across the basin we'd be thrilled, please. But most of that has not been accessible, and there was a related question below about sort of coordination with industry. And when Pioneer was operating in the field, we corresponded with Hal McCartney a bit, and he was very helpful to the extent that he could share things, but that was pretty limited. And so we'd talk about things in person and look at some figures, but it wasn't stuff that we could use in open access research. And so that's kind of the only sphere that is relevant to us. Otherwise, it's kind of hard for students to publish their work. And so we haven't really ventured into trying to use anything that isn't in the open access realm.
Question for both of you about that. The project I work on at the USGS is making detailed digital geologic map compilations, and they've already covered the Raton Basin area. I'm wondering what kind of detail you would need for that to be useful, because creating a balanced cross section is very much within the realm of possibility.
Yeah, and with a more recent student, we've been working on trying to map the sediment basement contact and look at things, but most of the faults that we're interested in here that are seismogenic are down in Precambrian basement. And so whether they have any expression in the sedimentary strata or at the surface, it's likely they don't. And so, we're reactivating potentially very old structures, and I don't know what indications we'd pick up from maps. So I think the structural model would probably have to come more from well data and controlled source imaging, things like that. And we haven't found a great supply of it that's available to us.
Well, we're a few minutes past the end of the scheduled hour. There's a few more questions, but Brandon and Margaret, if you're willing to kind of stick around for a few minutes, maybe we can have more of an informal discussion, including I think I misrepresented Stan's question about so we could maybe get into the details and get clarity there if you're willing to stick around. But I guess good timing to wrap up the formal part of the webinar. So on behalf of ARMA, I'd like to thank both Margaret and Brandon for presenting today, and all the participants for joining us. Another great webinar in the series. So thank you very much. Just a reminder to everyone, October presenting on Kansas observations. So I'm sure Mike will have lots of interesting stuff to say, and just keep in mind, you'll see the invitation coming from Madi, but as normal, but again, it's not the first Friday of the month. We're going to go for the second Friday, the 13th. I think Mike just likes Friday the 13th. Maybe that's why he picked the day. Okay, well, thank you, everybody. Have a good day, and thanks again, Margaret and Brandon.
Thanks.
Thank you.
Are you guys able to stick around, and maybe we could ask the other question?
Margaret may have some flexibility. I should already be in another meeting, and so that's unfortunate. If there are anybody who wants to talk about this stuff, please get in touch by email. I'm excited about it and appreciate the feedback, but at the moment have to run.
Great, thanks, Brandon.
Thanks, Brandon.
I can stay.
Thanks, Margaret. I don't know if Tom, looks like you're still on, and Brandon kind of referred to your talk, but do you have any kind of follow-up questions for the industry collaboration? feel free to unmute Tom if Moustic if you want, or
Yeah, I was just curious whether there had been any cooperation with the industry, because I'm aware of private local networks that are out there, and whether there's been any analysis of any of the seismic reflection data that might be available from the industry side.
I think, yeah, Brandon answered it fairly well. Is all of the data there is private, so we haven't worked with them, but we've seen some of the figures that they have for their earthquake catalog. So they're happy to talk with us, but because the data is private, we just can't. We could do a lot of research, but we couldn't publish it. So yeah.
Okay.
And I've heard that there are seismic reflection profiles from a while ago, but I think that those are sort of just outside of the area that we're looking at. But if anybody knows of seismic reflection data that's publicly available, or a figure or something, please email it to me.
Margaret, just an aside on that, now that you're with USGS, it's possible that the energy group has seismic reflection data, usually it's old. And I've had some luck with that in Nevada, and depending on budgets, sometimes they're able to buy really old seismic reflection data. There are people who have access to all the databases and so on, but there might be avenues to go through.
Cool, thanks. Yeah, I hadn't thought of that. I have changed organizations, so yeah, check with them.
Got access to the secret USGS library too, all information. So Sandeep Mahajan has a question in chat, and Sandeep, I think you're still on. Would you like to unmute and ask the question?
Hi. I think anywhere in your slides, I think you showed the pre-shocks, aftershocks, and I think cessation of the seismicity after reducing the rate. If I just think back fundamentally, I think it's the pressure increase on the fall that will induce the slip. And then when you drop the rate, the pressure is still increasing, but probably the rate of increase of pressure is significantly lowered. So my question was, the seismicity keeps happening at a lower magnitude or lower count. But when we plan, I work for Shell, but when we plan the developments, let's say CCS or injection, it's always a question, what's the rate we should plan and how many wells? So is there some guideline, or in this result, did you find what was the pressure rate increase prior to that big event and what was the pressure rate increase? So because if we know what the pressure could increase at what rate with time, that could be something that feeds into the development of injection.
Thanks for the question and the idea there. I think that we are just very limited on the wastewater injection data, so 1 sample per month. And then also, as Brandon sort of mentioned, the correlation between the earthquake rate and the injection, it's hard to pin down. Like, for example, if there's a lag and what the lag is, and if that could be different in different areas. So I think it's just a sort of tough problem to solve, if that makes sense.
Yeah, because I think predicting the magnitude is always very hard, but keeping the magnitudes on check could be something that could be driven for the development by, for example, for this system, a pressure rate increase of X MPa per year, probably the risk of inducing. I mean, it's a slow kind of system. And if you exceed this rate of pressure increase, then something like that. I think I was trying to get to like how we use this data or information and results to plan the future developments.
Yeah, I've thought about that. Like when you look at the earlier records, so we don't have our record of the seismicity for the area begins in 2008 when we have a nearby station. But if you look at this time when the injection was even higher and there was this first earthquake up here to the north, but even the blue area, so these wells were injecting as high as they were
Correct.
before the 5.3, but nothing above, no significant magnitude, nothing above a 4 was happening in this area. So yeah, it would be cool though to come up with something, like a probability of having a large event, given whatever the wastewater injection rate was. But I think that would be really individualized to, kind of understand the each fault. But then it's always tough because new faults are being reactivated. So yeah, it's just such a complicated problem. Recently these areas have become active, but there hasn't really been a change in the wastewater injection right there. So
Margaret, I'm guessing that the Raton Basin would be especially hard for that to do that kind of thing. I mean, that's one of the key sorts of ideals that we'd be able to put magnitudes on these things. And I'm guessing with the earthquake triggering problems in the Raton or issues that presents a problem, and maybe Oklahoma would be an easier place to try something like that. What do you think, having worked in this basin so much?
Yeah, that's a good question. I think I'm not familiar enough with Oklahoma, Kansas, although I'm starting to become more familiar with it. And it's really showing me how different Raton is. I think that there, I know if you look at sort of this bigger picture, you see a very strong correlation with the peak in seismicity, with the peak in wastewater injection, maybe a 6-month lag. And then as wastewater injection rates decrease, there appears to be a clear decrease in the seismicity there. So it does seem more like neatly tied to the wastewater injection. Whereas here it's just hard to say when a sequence is over, I think, in this area. So that magnitude 5.3, there's earthquake activity there for years following on faults that had been activated during the magnitude 5.3 or triggered right after. And so it's kind of hard to say when was the end of that sequence. And I'm not sure what that looks like in Oklahoma, Kansas, but saying which one was actually induced from the wastewater injection and which ones are from a natural process of earthquake interactions, but originally started or were caused by the increased pressure from the wastewater injection. So I think I just talked myself into a circle. Sorry.
And that's good. Stan Wasowski, I think Stan's jumped off, but I think I fear I misrepresented his question. He was actually asking about the E-test modeling and stationary versus non-stationary E-test models, I think. Are you there, Stan? I think he's gone.
I think he's gone, but I did want to, especially for the question to just to clear the record, could you comment that in relation to your conclusion that the seismicity is predominantly tectonic? I don't think that the seismicity is tectonic. I think that there's nothing special at the scales that we looked at about the seismicity to say oh, this indicates that these events were induced. As far as, not particularly swarmy. The nearest neighbor distribution was bimodal with nice distributions on either side of background and clustered, similar to a tectonic area. So I think sometimes that point can easily be misinterpreted to be that we're saying the earthquakes are tectonic, more just that the induced earthquakes aren't, we haven't found any sort of statistic that can tell us that they're induced. But just this plot here is telling us, I think if we didn't have the wastewater injection, we wouldn't have the earthquakes. So, or we wouldn't have them very often, maybe 1 or 2 during this whole time period.
So Margaret, you didn't focus too much about the northern basin events in the sort of detailed analysis. Some of the earlier slides showed some less active clusters to the north. But I was wondering, do you think those might be tectonic, or do you think they're induced but not as well monitored?
I think that they are induced and they just don't fall in such, not as many sort of reactivated pieces are there. There's just smaller sort of faults. So not as extensive as, sort of these zones. But there are like quite a few clusters up here to the north. And I have wondered a lot about that, especially the ones that fall outside of the basin outline. So the outline of the basin is based on where the layer that the methane's produced in, but the injection is deeper than that. And I will just, towards the north is the area where, if there has been any sort of temporal correlation with the seismicity and wastewater injection, I feel like there are some hints of that actually in the north. I think maybe in some ways, because it's not as many fault systems, you might be able to sort of see potentially that forcing more clearly. So especially in the northeastern part. And I think I know I looked into that before the 2021 paper, but I don't think too much of that went into the actual paper. So yeah, I'm interested in the seismicity to the north. There's a good bit of it. We focused on the areas where the majority of the seismicity is. We have 90% of it is like in these two zones. So
is that the Spanish Peaks area that we see?
Yeah, so the Spanish Peaks, they're right here. So they're and our seismicity, so these are those two seismometers you can see on the other map. The closest to the Spanish Peaks would be right here, but a lot of the seismicity sort of is a little bit more to the northeast.
I have a question. Margaret, great presentation. So is the injection happening at the same interval as the hydrocarbon production is?
Is the injection happening at the same?
At the the depth interval as the production is, hydrocarbon production is done?
No, the production is actually shallower. That's not on here, but it's it's even shallower by half a kilometer or kilometer, depends on where you are in the basin.
So it is an unconventional reservoir, the production interval? Is that like a low permeability formation?
The production interval?
Yeah.
I don't know that much about it. I know it has a lot of coal bed seams, methane seams. So, and you can see them like outcropping at the surface, which is kind of cool when you go to collect data or put a seismometer in.
Sure. So how good you can predict the depth of the event? Do you have good velocity model to say the event is happening in either of these intervals?
Well, most of the seismicity happens much deeper by a few kilometers. So I think we know that it's, in the basement. So we haven't constrained that well. The velocity model is just a 1D model. I wouldn't say that it's very good. It would be awesome to have something that was 3D. Yeah, and I don't think it's been updated. There hasn't been any new information to update it that anyone's used since we used a model that was used in a 2014 study of seismicity by Rubenstein.
Thank you.
But I mean, we don't think, we think for the most part, our depths are, I'd say plus minus 0.5 kilometers. So.
Plus you have the relative locations.
And then the relative locations are, the error on those are smaller than 200 meters for relative.
Mhm.
When Hal McCartney was around working this area, I think he had some work done on just reprocessing different velocity models, and if I remember right, the conclusion was that similar to what you just said, they're deep events. Despite the head scratching nature of why relatively shallow injection has such deep activity in the basement, seems exactly that, a head scratcher, right?
Yeah. Yeah, it would be, as Brandon mentioned, it'd be interesting if we could see the faults and see if they cut basin sediment, would be very interesting. But that's like in the dream list.
We see a similar pattern in, you know, enough other places that it's not too unusual.
The injection in Oklahoma, though, it's pretty close to the basement, right?
Yes, that is true.
Okay, I'm not as familiar with other places, you know, so I'm starting to learn how to place this in the context of other areas.
It's hard to generalize, but I think in a lot of areas the seismicity is closer to the top of basement, but it's the same problem everywhere. Can we trust the velocity model, and how much zero offset stations do we have to constrain the depth?
Mm.
Does anybody have any other questions? If not, maybe we can let Margaret get back to her day job. But thanks a lot for presenting. This was a great overview, and appreciate your help.
Oh yeah, thanks for having us. We were excited to give the talk, and yeah, it was fun. I hope people enjoyed it, and always happy to talk more about it if anybody wants to.
Sounds like we'll have
Thank
to
you,
get
Margaret.
to talk about the tidal-induced activity in Kansas and Oklahoma as well, once you get down the road a bit.
Yeah, I hope it's a good project. It might end up being a little bit less exciting. It might be that there's a very slight signal from that, but yeah, keep your eye out. Oh, and also the other paper for the final part, I should have said it was just published 2 weeks ago. I should have probably tried to highlight that slightly more, but yeah.
You just did. The recording will be seen by a lot of people, and they refer to that.
Oh, okay, cool. That's right, because they can find it if they want to. So
yeah.
Cool. Thank you so
Thank
much.
you so much.
This is one of my favorite webinar series. So hopefully that's a nice compliment for y'all. I really enjoy it.
Thank you.
Thank you so much. Have a good weekend, everyone.
Yeah, have a good one. Thanks, everyone.